When a massive star dies, it can collapse into one of the strangest objects in the universe, a neutron star. How do these stellar remnants form? What are they made of? And what secrets still puzzle scientists today? In this video, we'll explore it all. If you enjoy cosmic mysteries, please like, subscribe, share, and tell us in the comments what fascinates you most about neutron stars. Thank you for watching. Now, let's begin. A neutron star begins its existence in the death of a massive star. A massive star spends millions of years producing energy in its core by fusing lighter nuclei into heavier ones. Each stage of fusion adds a new layer of elements, with hydrogen burning to helium, helium to carbon, and eventually carbon and oxygen to heavier products. The process continues until the star produces iron in its core. Iron cannot release energy through fusion, and once it dominates the core, the balance that supports the star fails. The hot radiation pressure that once countered the force of gravity is no longer maintained. The outer layers press down with overwhelming weight, and the star's central regions collapse. In only a second, the density of the core rises to values far beyond ordinary matter. Electrons are squeezed into protons, combining to form neutrons through inverse beta decay. The collapse halts when neutron degeneracy pressure comes into effect. This pressure arises from the Pauli exclusion principle, which states that identical particles such as neutrons cannot occupy the same quantum state. The particles resist further compression not through ordinary forces, but because quantum rules forbid identical particles from being forced into the same conditions. This sudden resistance stops the collapse, and the core becomes an object made predominantly of neutrons. The outer layers, still falling inward at enormous speeds, strike the now rigid core. The collision releases shock waves, and with the help of intense neutrino emission from the dense matter, these shock waves reverse the infall. The star's envelope is blown outward in a supernova explosion. The light from this event can briefly outshine an entire galaxy, though much of the true energy is carried away by neutrinos escaping from the dense interior. Left behind in the center is a compact remnant with a mass typically between 1 and 2 times the mass of the Sun, compressed into a sphere only about 20 kilometers across. This new object is called a neutron star. Its density is so extreme that a teaspoon of its material would outweigh a mountain. At birth, it is fantastically hot with temperatures of billions of degrees. Radiation pours from its surface as it begins to cool. In the first moments, the neutron star radiates in neutrinos which carry away heat much faster than photons. Over thousands of years, the surface temperature declines from billions to millions of degrees, leaving the star glowing primarily in X-ray wavelengths that space telescopes can detect. The violent birth leaves other imprints. The newborn neutron star often spins rapidly, since the progenitor star's rotation is conserved as the collapsing core shrinks. What was once a slow rotation of the entire star becomes a spin measured in milliseconds or seconds. The collapse also amplifies the star's magnetic field. A massive star may have had a field of hundreds of Gauss, but once compressed, the same field lines are concentrated. The surface field of a neutron star often reaches trillions of Gauss, strong enough to shape its radiation and interaction with space plasma. The neutron star may also receive a kick from the asymmetric explosion. Observations show that many neutron stars travel through space at hundreds of kilometers per second, far faster than ordinary stars. These natal kicks are thought to arise from small imbalances in the supernova shock or in neutrino emission. Whatever the cause, the result is that neutron stars can be hurled across galaxies drifting alone, or even escaping their birth galaxies entirely. The setting of the birth is marked by the supernova remnant. Expanding clouds of gas enriched with heavy elements spread into interstellar space. The remnants observed by telescopes such as the Crab Nebula or Cassiopeia reveal glowing shells energized by the shock waves of the explosion. Within them, neutron stars can sometimes be observed directly, either as pulsars flashing in radio and X-ray beams, or as compact hot points of emission. These associations confirm the link between massive star collapse and the birth of neutron stars. The physics of the transition is complex and not yet fully understood. Computer simulations attempt to model the moment when the shock front revives and the star explodes, but details remain debated. Neutrino transport turbulence and the role of magnetic fields all influence the final explosion. Yet the outcome is clear: without the collapse of massive stars, neutron stars would not exist. It is also important to note the boundary conditions. Not every core collapse produces a neutron star. If the progenitor star is too massive, the collapsing core can exceed the maximum mass that neutron degeneracy pressure can support. In such cases, no stable neutron star is possible, and the core collapses further to form a black hole. The dividing line is still uncertain, but present models suggest that stars with initial masses greater than about 20 to 30 times the mass of the Sun are more likely to leave black holes, while those in the lower part of the massive star range leave neutron stars. This uncertainty ties back to the nuclear physics of dense matter and the efficiency of the supernova explosion mechanism. Observations of young neutron stars confirm their extreme conditions. Some are seen spinning dozens of times per second, others show giant magnetic activity. Their environments are rich with clues about their creation. In remnants where neutron stars are not found, astronomers infer that a black hole may have been formed instead. Thus, the cosmic census of supernovae and their remnants provides a way to study the outcomes of stellar death. The idea of matter compressed to neutron density was first suggested in the 1930s, soon after neutrons were discovered. But it took decades of astronomical observation to confirm their reality. The detection of pulsars in the 1960s finally provided strong evidence. These objects were too small to be ordinary stars, yet too massive and stable to be white dwarfs. Only neutron stars fit the data. Since then, studies of supernova remnants, X-ray sources and gravitational waves have continued to enrich the picture of how neutron stars form. In the vast timescales of the universe, neutron stars are short-lived in their hot luminous stage, but they remain as compact remnants for billions of years. The cooling process continues steadily, and their visible brightness fades. Yet their imprint on the galaxy endures. Supernovae distribute the elements forged in the progenitor star-seeding future stars and planets. The neutron star itself becomes a laboratory of dense matter physics, carrying forward the conditions of its creation. From the viewpoint of astrophysics, the formation of a neutron star is one of the most dramatic compressions of matter nature allows before crossing into the black hole state. Gravity, nuclear forces, and quantum mechanics all converge at once. The product is an object smaller than a city yet heavier than the Sun, marking the end of one star and the beginning of a new kind of celestial body. When a neutron star is born from the collapse of a massive star, it inherits physical conditions that shape its evolution. These properties established at birth include its spin, its magnetic field, and its velocity through space. Each of these features results from the conservation of physical laws during collapse and from the chaotic processes of the supernova itself. Together they form the basic characteristics by which neutron stars are observed today. The spin of a neutron star arises from angular momentum conservation. A massive star rotates slowly during its life, often completing a turn in days or weeks. When its core collapses into a neutron star only about 20 kilometers across, that angular momentum is preserved. Just as a spinning skater rotates faster when pulling in their arms, the shrinking of the star's radius increases its rotational speed. Newly formed neutron stars can spin several times per second, and some can rotate hundreds of times each second. These spin rates define much of their observable behavior. The rapid rotation drives strong electric fields, influences the emission of radiation, and determines how the star interacts with its surroundings. Spin is not constant throughout a neutron star's lifetime. Over time, electromagnetic radiation and particle winds carry away energy and angular momentum. This slows the star's rotation, a process called spin down. By measuring the gradual change in a pulsar's rotation rate, astronomers can estimate its age and energy loss. Some neutron stars are born spinning relatively slowly, while others begin with extraordinary speeds. The diversity reflects differences in the angular momentum of their parent stars and in the details of the collapse. Magnetic fields are another defining property. The magnetic field of a neutron star is inherited from the progenitor star, but becomes vastly stronger during collapse. The compression of magnetic field lines concentrates their strength. Where a normal star may have fields of a few hundred or thousand Gauss, the compact remnants fields are amplified to values of trillions of Gauss. For comparison, Earth's magnetic field at the surface is about half a Gauss. This enormous amplification makes the neutron star environment unlike anything else in the universe. The field governs how charged particles move near the star shapes, the radiation beams that make pulsars visible, and stores immense amounts of energy that can be released in bursts and flares. The strength of the field at birth is not uniform. Some neutron stars emerge with fields in the range of 1 trillion Gauss, while others develop even stronger fields exceeding 1 quadrillion Gauss, becoming magnetars. The origin of such variation is not fully resolved. It may involve the rotation rate of the collapsing core turbulence during collapse, and processes similar to dynamos that generate magnetic fields. The diversity of magnetic strengths means that neutron stars can evolve along different observational paths. In addition to spin and magnetic field, neutron stars are often imparted with a velocity kick at birth. Observations of pulsar motions across the galaxy reveal that many travel at speeds of hundreds of kilometers per second. Some are fast enough to eventually leave the gravitational pull of the Milky Way. These high speeds cannot be explained by simple orbital mechanics of their parent stars alone. Instead, they are believed to result from asymmetries in the supernova explosion. If the explosion is not perfectly spherical, the remnant can recoil in the opposite direction. Another possible contribution comes from anisotropic emission of neutrinos, though this remains debated. Regardless of mechanism, the observed velocities demonstrate that neutron stars can be displaced far from their birthplaces, scattering across galaxies and populating interstellar space with solitary compact remnants. The combination of spin magnetic field and kick velocity defines the trajectory of a neutron star's early life. A rapidly spinning neutron star with a strong magnetic field can become a bright pulsar emitting beams of radiation that sweep across space like a cosmic lighthouse. A neutron star with weaker fields or slower rotation may remain more difficult to detect, glowing faintly in X-rays as it cools. Those ejected at high speeds may travel alone, while others remain in binaries where their future is governed by the interaction with a companion star. Astronomers study these birth properties through multiple observational channels. Radio telescopes measure the periodic signals of pulsars, revealing their spin rates and spin down. X-ray observatories detect thermal radiation from hot surfaces and burst from accreting stars. Optical telescopes capture the motion of neutron stars relative to background stars, allowing their velocities to be traced. Gravitational wave detectors now provide information on merging systems, which indirectly reveals the distribution of masses and birth characteristics. Each instrument adds a piece to the picture of how neutron stars emerge from supernova. The importance of these properties extends beyond individual objects. By building a census of neutron stars, astronomers can study the population as a whole. They can ask how many are born rapidly spinning, how many are given large kicks, and how many retain their magnetic intensity over long timescales. These questions link back to the physics of supernova explosions and the uncertain details of core collapse. If asymmetries in explosions are responsible for kicks, then understanding kicks helps constrain how the explosions function. If magnetic fields are set by dynamo action during collapse, then measuring the distribution of fields reveals how matter behaves under extreme compression. Uncertainty remains particularly about the maximum spin a neutron star can sustain, and about the true limits of magnetic field generation. Theory suggests that neutron stars cannot spin faster than about 1,000 times per second without breaking apart due to centrifugal force. Observations confirm that the fastest known spin rates approach, but do not exceed this limit. For magnetic fields, the upper end appears to be magnetars with fields around a quadrillion Gauss. Why the distribution peaks at certain values is not yet settled. Birth conditions also affect neutron star lifetimes. Rapidly spinning stars lose energy more quickly, slowing down, and sometimes producing strong winds that can sweep away surrounding material. Those with extreme magnetic fields undergo violent flares that fracture their crusts. Meanwhile, neutron stars with large kick velocities can be thrown into sparse regions of space, where they cool in isolation and fade from detectability. The initial imprint of the collapse thus sets the path for the star's entire existence. The study of birth properties is made challenging by the speed with which they evolve. Within tens of thousands of years, a neutron star may lose much of its surface heat, making it difficult to detect. Spin and magnetic field strength also decay over millions of years. Astronomers must therefore combine observations of young remnants in supernova shells with surveys of older, more evolved neutron stars to reconstruct the range of initial conditions. This requires long-term monitoring and coordination between many observatories. Despite the uncertainties, the broad picture is secure. Neutron stars emerge from supernovae with extreme spins, intense magnetic fields, and velocities that often exceed those of normal stars. These properties are not incidental but essential to their nature. They dictate how the star will cool, how it will radiate, and how it will interact with its surroundings. They also provide insight into the supernova explosion mechanism itself, which remains one of the most complex and active problems in astrophysics. By continuing to study the youngest neutron stars, astronomers refine models of how massive stars die and how compact remnants are born. The interior of a neutron star cannot be seen directly, yet it defines the star's behavior and structure. The relation between pressure and density inside the star, called the equation of state, is central to understanding what neutron stars are. An equation of state describes how matter responds to compression, giving the balance between inward gravity and outward pressure. For neutron stars, this balance is pushed to the edge of known physics. The densities in the core reach several times that of atomic nuclei. Under such conditions, particles behave in ways that cannot be reproduced in laboratories on Earth, so the equation of state must be inferred from theory and observation together. The equation of state determines the possible radius of a neutron star for a given mass. If the matter inside is relatively stiff, meaning that pressure rises strongly with density, then the star can resist compression and maintain a larger radius. If the matter is softer, the pressure increases less with density, and the star becomes more compact. Observations of neutron star radii combined with their masses therefore provide constraints on the true equation of state. This is why measuring neutron stars is not only about describing exotic objects, but also about probing fundamental nuclear physics. At densities around the nuclear saturation point, neutrons and protons interact strongly, and theoretical models must incorporate the complexities of nuclear forces. At higher densities above several times nuclear density, additional possibilities emerge. Some models suggest that hyperons particles containing strange quarks could appear in the core. Others propose that deconfined quark matter, where neutrons and protons dissolve into a sea of quarks, may exist in central regions. These states of matter are not accessible in terrestrial experiments and remain a frontier of theoretical physics. The existence of such exotic cores would soften the equation of state, shrinking the star and lowering the maximum mass it can support. The maximum mass a neutron star can hold before collapsing into a black hole depends directly on the equation of state. Observations of massive neutron stars therefore provide important constraints. Several pulsars with masses around 2 solar masses have been measured through their influence on companion stars in binary systems. These discoveries rule out equations of state that cannot support such heavy objects. The precise upper limit remains uncertain, but most estimates place it between 2.5 and 3 solar masses. If a core left behind by a supernova exceeds this threshold, no stable neutron star can form, and the collapse continues to a black hole. Gravitational wave astronomy has added a new tool for probing the equation of state. When 2 neutron stars spiral toward each other and merge, the way they deform under each other's gravity encodes information about their internal structure. This effect, called tidal deformability, changes the waveform of the gravitational radiation. By measuring it, observatories like LIGO and Virgo can set limits on how stiff or soft the equation of state must be. The first observed binary neutron star merger in 2017, known as Gibeon Center 7, provided such constraints, pointing toward radii of about 11 to 13 kilometers for typical neutron stars. Another line of evidence comes from X-ray observations. The NICE mission on the International Space Station has measured the pulsed X-ray emission from neutron stars with high precision. By modeling how light bends in the strong gravity near the surface and how hotspots on the surface rotate in and out of view, NICE can infer the radius of the star. Results so far suggest radii around 12 kilometers for stars of about 1.5 to 2 solar masses, consistent with the gravitational wave findings. This convergence of independent methods strengthens confidence in the emerging picture of the equation of state. Still, questions remain open. The behavior of nuclear forces at high density, particularly the role of 3-body interactions, where 3 nucleons influence each other, simultaneously introduces uncertainty. Laboratory experiments using heavy ion collisions can recreate matter at high temperature and moderate density, but not at the cold, ultra-dense conditions of neutron star interiors. Thus, astronomers must continue to rely on the stars themselves as natural laboratories. Each new observation helps narrow the possibilities. The equation of state is not only a theoretical curiosity, it affects observable phenomena such as the frequency of oscillations in neutron star crusts, the pattern of thermal emission as the star cools, and the dynamics of mergers. If exotic matter like deconfined quarks exists in the core, it could lead to characteristic signals in gravitational waves or in sudden transitions during the star's spin evolution. Some models predict that the inner core might undergo phase changes, shifting between different states of matter as pressure and density change. Such transitions could release bursts of energy detectable across space. Neutron stars therefore stand at the intersection of astrophysics, nuclear physics, and particle physics. Their equation of state is not simply a property to be measured, but a doorway into understanding matter under the most extreme conditions known. Theoretical work continues to refine models, while astronomers search for more massive neutron stars, observe more mergers, and improve radius measurements. Each step brings closer a resolution to the question of how matter behaves when compressed to densities far beyond those of atomic nuclei. The uncertainty itself is part of the story. Unlike ordinary stars where the physics of fusion is well understood, neutron stars force scientists to confront unknown regimes. The pressures are so great that protons and neutrons may lose their identity. Quarks may roam freely and entirely new forms of matter may exist. Whether these states are realized in nature is not yet settled, but the possibility ensures that neutron stars remain among the most intriguing objects in the universe. The surface of a neutron star is unlike that of any other stellar object. Instead of being a glowing sphere of gas like the Sun, it is bound by a thin but exceptionally strong crust. This crust, only about 1 kilometer thick, serves as the outer layer of the star. Although it is narrow compared to the overall radius of 10 to 12 kilometers, it is fundamental to the star's behavior. The crust is composed of nuclei arranged in a crystalline lattice, immersed in a dense sea of highly energetic electrons. Gravity at the surface is unimaginably strong, more than 100 billion times that on Earth, so the crust must resist pressures no terrestrial material could survive. At the very top of this outer crust, where densities are still relatively low by neutron star standards, the material resembles extremely compressed ordinary matter. Iron nuclei are thought to dominate because iron is the most stable nucleus produced in stellar evolution and supernova explosions. These iron nuclei form the initial solid layer that acts as the skin of the star. Just beneath the pressure increases rapidly. Electrons are forced to higher energies, and the balance of nuclear stability shifts. Nuclei begin to capture electrons, converting protons into neutrons, and the crust becomes populated by neutron-rich isotopes that cannot exist on Earth. As the depth increases, so does the density. At around 1 billion times the density of water, the lattice contains exotic nuclei stretched to extreme neutron excess. The further one descends, the more neutrons are squeezed into nuclei until the point is reached where neutrons begin to drip out of the nuclei altogether. This marks the transition into the inner crust, but the outer crust itself is still remarkable. It contains a sequence of layers, each stabilized by the specific balance of nuclear and electronic energies at that depth. Theoretical models predict which isotopes dominate at which pressures, but the details remain an active area of research. The outer crust is rigid, and this rigidity shapes how the neutron star interacts with its surroundings. Unlike the fluid interiors of normal stars, the crust can support stress. It can hold up tiny irregularities called mountains, though in reality these are only centimeters to meters tall. Under the gravity of a neutron star, such small deformations are significant. As the star rotates, they create time-varying mass distributions that can emit continuous gravitational waves. This possibility motivates searches with gravitational wave observatories, which might one day detect signals from mountains on spinning neutron stars. The crust also acts as a store of elastic energy. As magnetic fields and rotational dynamics stress the crust, it can fracture suddenly. These events, known as starquakes, release stored energy and cause small but abrupt changes in the star's rotation. Astronomers detect these as glitches in the regular timing of pulsars. Such glitches provide evidence that the crust is not a passive boundary, but an active participant in the dynamics of the star. Each glitch is a clue to the internal stresses, the distribution of superfluid components beneath, and the coupling between different layers of matter. Cooling of neutron stars also depends on the crust. When a neutron star is newly formed, its interior is extremely hot at billions of degrees. Neutrinos carry away energy rapidly, but over longer timescales the flow of heat to the surface is regulated by conduction through the crust. The composition and crystalline order determine how easily heat is transported outward. Astronomers use observations of cooling rates in young neutron stars to infer crustal properties. One striking example is the neutron star in the Cassiopeia, a supernova remnant which has cooled measurably over the last 2 decades. The pattern of this cooling is consistent with changes in the interior superfluid, but the way the surface responds depends critically on the crust. Magnetic fields anchored in the crust introduce further complexity. The magnetic field lines of a neutron star are tied into the crystalline lattice, and as the field evolves, stresses accumulate. In ordinary pulsars, this can lead to gradual spin-down and mild activity, but in magnetas the fields are so intense that the crust is repeatedly fractured. These fractures release bursts of X-rays and gamma rays that can outshine entire galaxies for brief moments. The strongest magneta flares observed have released energy equivalent to the total output of the Sun over thousands of years, yet the trigger is the breaking of a crust only a kilometre thick. The outer crust is also a site of ongoing nuclear reactions in neutron stars that accrete matter from companions. When hydrogen and helium from a companion star fall onto the neutron star surface, they undergo nuclear fusion under extreme compression. These reactions produce heavier nuclei that are gradually pushed downward into the crust. As fresh layers build up, deeper regions are buried and compressed, driving electron captures and neutron emissions that alter the composition. This process replenishes the crust, continually making accreting neutron stars dynamic laboratories of nuclear physics. Thermonuclear explosions on the surface, seen as X-ray bursts, are one consequence of this cycle. Theoretical work extends the understanding of the crust into unusual phases of matter. At certain densities, the competition between nuclear attraction and Coulomb repulsion is predicted to produce exotic structures known as nuclear pasta. Instead of spherical nuclei, matter may form rod slabs or bubble-like configurations. The names spaghetti, lasagna, and Swiss cheese have been given to these phases. They are not fanciful inventions, but plausible results of energy minimization in extreme conditions. Nuclear pasta may strongly affect how magnetic fields move and how heat is conducted. Simulations suggest that these structures could be extraordinarily strong, perhaps the toughest material in the universe. Astronomers cannot see the crust directly, but they study it through indirect signals. Pulsar glitches tell of sudden shifts in the balance between crust and superfluid. Magneta flares reveal catastrophic fractures driven by magnetic stress. Thermal emission from cooling neutron stars provides evidence for conductive properties. X-ray bursts in accreting systems highlight the fresh nuclear reactions that continually rebuild the surface. By combining these observational threads, researchers piece together a picture of the crust's composition, structure, and role. Even though the crust represents only a small fraction of the neutron star's thickness, it controls much of what can be detected across interstellar distances. It stands between the invisible core and the observable sky, mediating signals of heat rotation and magnetism. Its lattice of exotic nuclei, its interactions with magnetic fields, and its response to stress all make it essential to understanding how neutron stars behave. Beneath the rigid outer crust of a neutron star lies the inner crust, where matter begins to take on properties that are entirely unfamiliar to terrestrial experience. At this depth, the pressure is so extreme that nuclei become heavily neutron-rich. Electrons are continually forced into protons, converting them into neutrons, and eventually neutrons begin to leak out of the nuclei. These free neutrons do not behave like a normal gas. Instead, they condense into a superfluid, a quantum state of matter that flows without viscosity. The inner crust is therefore a hybrid region, where a lattice of neutron-rich nuclei coexists with the sea of superfluid neutrons and relativistic electrons. This superfluid state arises because neutrons, like electrons, are fermions. They obey the Pauli exclusion principle, which prevents identical fermions from occupying the same quantum state. However, under the extreme conditions of the inner crust, neutrons can pair up in a way that allows them to act collectively. These pairs are called Cooper pairs, and they behave like bosons rather than fermions. Bosons can share the same quantum state, so the ensemble of paired neutrons condenses into a macroscopic quantum state, a superfluid. In this state, neutrons can flow without resistance, moving through the lattice of nuclei and electrons with no friction. The presence of superfluid neutrons has profound consequences for the behavior of neutron stars. One of the most direct observational effects is seen in pulsar glitches. Pulsars are rotating neutron stars whose beams sweep across Earth, producing highly regular pulses. Sometimes, however, their rotation rate suddenly changes. These glitches are interpreted as transfers of angular momentum between the superfluid in the inner crust and the rigid lattice. The superfluid can store angular momentum in the form of quantized vortices, tiny whirlpools constrained by quantum mechanics. When these vortices suddenly unpin from the lattice of nuclei, the superfluid transfers some of its momentum to the crust, causing the star's rotation rate to jump. Such events confirm that superfluidity is not just a theoretical idea, but an active feature of neutron star interiors. The superfluid also affects how neutron stars cool. In ordinary matter, heat is carried away by particles colliding and scattering. In a superfluid, the situation is different. The formation of Cooper pairs releases energy in the form of neutrinos, accelerating the cooling process. At the same time, the presence of the superfluid alters how thermal energy is transported. Observations of neutron stars cooling over decades have been used to infer the onset of neutron superfluidity, particularly in the young neutron star of Cassiopeia A. Its rapid decline in temperature suggests that neutrons in its interior began pairing up into a superfluid within the last few centuries. The inner crust also introduces another exotic component, superconductivity. While neutrons form a superfluid, protons, though far fewer in number, can form a superconducting fluid. Superconductivity is the quantum state in which charged particles move without electrical resistance. In the inner crust and deeper into the core, superconducting protons coexist with superfluid neutrons. This mixture is unique in the universe. It has no direct analogue on Earth since it combines electrical superconductivity with neutron superfluidity under immense pressure and density. The interaction between these two states is thought to shape the magnetic field of the neutron star and may influence the long-term evolution of its spin. Another predicted phenomenon of the inner crust is the presence of nuclear pasta. While the outer crust contains spherical nuclei in the inner crust, the extreme pressures distort these nuclei into unusual shapes. Nuclear attraction favors clustering while Coulomb repulsion resists. The compromise produces rod-like or slab-like structures that extend through regions of the inner crust. Simulation suggests that these structures can be extraordinarily strong, surpassing the tensile strength of steel by many orders of magnitude. Nuclear pasta may anchor magnetic fields and resist crustal deformations, influencing how and when starquakes occur. Its irregular geometry could also scatter neutrinos in distinctive ways, affecting the cooling behavior of the star. The interplay of superfluidity, superconductivity, and nuclear pasta makes the inner crust a highly complex environment. It is neither a uniform solid nor a simple liquid, but a mixture of phases with competing properties. Theoretical models attempt to describe how vortices in the superfluid interact with the nuclear lattice and with superconducting flux tubes of protons. These interactions determine how angular momentum is transferred and how magnetic fields evolve. Because such processes are governed by quantum mechanics on microscopic scales, but influence the star's global behavior, the inner crust is a bridge between the smallest and larger scales in physics. Astronomers cannot directly probe the inner crust, but indirect evidence supports its existence. Pulsar glitches provide strong hints of pinned vortices and superfluid reservoirs. Cooling curves imply the onset of superfluid transitions. Magnetar flares suggest that stresses anchored in the inner crust can trigger surface fractures. Each observational clue points to the inner crust as a vital region for understanding neutron star behavior. Laboratory experiments cannot recreate such conditions, so neutron stars remain the only natural laboratories for studying these states of matter. In accreting neutron stars where material falls in from a binary companion, the inner crust undergoes continual transformation. Fresh nuclei are deposited on the surface and gradually buried. As they descend into the inner crust, they undergo electron captures, neutron emissions, and pycnonuclear fusion reactions, where nuclei fuse due to quantum tunneling under pressure rather than thermal energy. These reactions release heat that is detectable when accretion pauses, allowing the crust to glow in X-rays. Such events, called X-ray transients, provide observational windows into the physics of the inner crust. They confirm that crustal reactions contribute significantly to the star's thermal balance. The study of the inner crust is a frontier where nuclear physics, condensed matter, physics, and astrophysics converge. Theoretical predictions must incorporate quantum mechanics, nuclear interactions, and relativity all at once. Superfluidity and superconductivity are familiar concepts from laboratory physics, but here they appear in conditions billions of times denser than earthly materials. Nuclear pasta is not just an amusing analogy, but a potential structural component of an astronomical body. By combining astrophysical observations with advances in nuclear theory and quantum simulations, researchers hope to build a coherent picture of the inner crust. At the very center of a neutron star lies the core, a region where matter reaches densities several times higher than those inside atomic nuclei. While the outer and inner crust can be described with some confidence using extensions of known nuclear physics, the core remains one of the least understood environments in astrophysics. The extreme pressures and densities force matter into forms not reproducible in any laboratory. Understanding what the core contains is crucial because it defines the maximum mass a neutron star can support and determines many of its observable properties. The outer layers of the core are believed to be dominated by a mixture of superfluid neutrons, superconducting protons, and relativistic electrons. Neutrons remain the majority particle, but a small fraction of protons and electrons maintain charge balance and allow the star to remain stable. These protons, though a minority, may play an outsized role because their superconductivity enables them to carry magnetic fields in quantized flux tubes. The interaction of these flux tubes with neutron vortices could affect both the magnetic and rotational evolution of the star, potentially linking pulsar glitches to the deeper core. At higher densities further inside, additional particles may appear. One possibility is the presence of hyperons, which are baryons containing strange quarks such as the lambda and sigma particles. Under extreme pressure, it becomes energetically favorable for neutrons to convert into these heavier particles. The appearance of hyperons, however, has a dramatic consequence. They soften the equation of state by providing new degrees of freedom for matter to occupy, reducing the pressure for a given density. This softening makes it harder for the star to support itself against gravity, potentially lowering the maximum stable mass. Observations of neutron stars with masses close to 2 solar masses place strong constraints on models that include hyperons, since those stars demonstrate that the equation of state cannot be too soft. Another possibility is that the core hosts deconfined quark matter. In normal nuclei, quarks are confined within protons and neutrons. At densities far beyond nuclear saturation, the separation between nucleons becomes so small that their quarks may no longer remain bound. Instead, they could form a quark-gluon plasma, or a more ordered phase of quark matter. Some models suggest that quarks might pair in color superconducting states, analogous to how electrons form Cooper pairs in superconductors. These exotic phases would change the pressure-density relation significantly. Whether neutron stars contain such matter remains uncertain, but if they do, it would represent a natural laboratory for physics beyond what particle accelerators can achieve. There are also proposals of hybrid stars in which the outer core is composed of neutrons and protons, while the inner core transitions to quark matter. In these models, the transition might be sharp like a phase boundary or gradual, with nucleons dissolving into quarks over a range of densities. Observationally, such transitions might leave signatures in the mass-radius relation of neutron stars, or in the behavior of stars undergoing collapse or merger. Gravitational waves from mergers may carry imprints of such transitions, as sudden softening or stiffening of the equation of state would alter the waveform. Some theories even consider the possibility of entirely strange quark stars. In these models, matter composed of up-down and strange quarks could be more stable than ordinary nuclear matter, leading to stars made entirely of strange quark matter. If true, some objects thought to be neutron stars might instead be strange stars. However, there is no observational evidence yet to support this scenario, and it remains speculative. Most astrophysicists regard it as an intriguing but unconfirmed possibility. The behavior of matter in the core also governs neutrino emission. Neutrino processes are the dominant cooling mechanism for neutron stars in their first 100,000 years. The rates of these processes depend on what particles are present. If only neutrons, protons, and electrons exist, then certain reactions called the modified Urca processes dominate, which are relatively slow. If additional particles such as hyperons or deconfined quarks are present, faster reactions become possible, leading to more rapid cooling. Observations of cooling neutron stars can therefore indirectly test which particles exist in their cores. The observed diversity of cooling rates suggests that different stars may have different internal compositions, depending on mass and other birth conditions. The stiffness or softness of the core equation of state determines the maximum neutron star mass. Observations of heavy pulsars such as PSR JL746 plus CISC20 with a mass over 2 solar masses provide strong lower bounds on how stiff the equation of state must be. Any model predicting maximum masses below these values can be ruled out. This makes massive neutron stars critical test cases for core physics. In the future, discoveries of even heavier neutron stars could further constrain which exotic particles, if any, can exist in their cores. The magnetic field also has its roots in the core. If protons form a superconducting fluid, magnetic fields thread the core in quantized flux tubes. Their interaction with neutron vortices could couple rotation to magnetism. This interplay might explain long-term changes in pulsar timing and in magnetar activity. The migration and rearrangement of flux tubes and vortices over long timescales could drive magnetic field evolution, although the details remain poorly understood. Another factor is the possibility of phase transitions in the core during the life of the star. If matter crosses a threshold where a new phase becomes energetically favourable, the transition could release energy or alter the star's spin. Some models suggest that sudden rearrangements in the core could trigger observable phenomena, perhaps contributing to giant magnetoflares or affecting the stability of stars near their maximum mass. Such transitions might also leave imprints in gravitational wave signals from mergers. Despite the uncertainties, progress is being made. Gravitational wave astronomy now offers a tool to probe the internal structure of neutron stars by measuring tidal deformability. The way a neutron star deforms under the gravitational pull of its partner during inspiral depends on its core equation of state. Observations from GW 817 already suggest that neutron stars are not extremely large, favouring moderately soft equations of state. Future detections will refine these limits. Meanwhile, X-ray timing missions like NICA measure neutron star radii with unprecedented precision, helping to distinguish between different core models. The neutron star core thus remains one of the most challenging frontiers in physics. It brings together nuclear interactions, quantum chromodynamics, superfluidity, superconductivity, and relativity. It cannot be recreated in laboratories, but nature has placed it within reach of telescopes and detectors. Each observation, whether of cooling glitches, bursts, or gravitational waves, adds a clue. By piecing them together, scientists gradually approach an understanding of what matter becomes when compressed to extremes beyond the atomic nucleus. Although the deep interior of a neutron star is hidden, the outer surface and the thin atmosphere above it are accessible to observation. The surface is not like that of a planet covered in rock or gas. Instead, it is a solid crust of exotic nuclei, and on top of this lies an atmosphere only a few centimeters thick. This atmosphere is composed of light elements such as hydrogen or helium, if the star has accreted material from a companion, or of heavier elements such as carbon and iron, if it is isolated and has lost its lighter layers. The properties of this atmosphere strongly affect how radiation escapes, shaping the thermal emission that astronomers detect with X-ray telescopes. Because gravity on the surface is so intense, the atmosphere is compressed to extreme densities. A neutron star's surface gravity is 100 billion times greater than Earth's. This means that the scale height of the atmosphere, the height over which pressure decreases significantly, is only about a centimetre. Light leaving the surface must climb out of a deep gravitational well, and in doing so it is redshifted. Photons observed at Earth have lower energies than when they were emitted, and the degree of redshift depends on the mass and radius of the star. This effect allows astronomers to probe the gravitational field directly by measuring spectral features from the surface. The surface is also shaped by the star's magnetic field. At strengths of trillions of Gauss, the magnetic field forces electrons and ions into quantized motions, altering how they absorb and emit radiation. As a result, the spectrum of surface emission is not that of a simple blackbody, but is modified by magnetic effects. In some neutron stars, absorption features in the X-ray spectrum have been interpreted as cyclotron lines, which occur when electrons spiral in magnetic fields. These features provide a way to measure the field strength directly at the surface. The geometry of emission is also unusual. Light leaving the surface is bent by the strong curvature of spacetime near the star. General relativity predicts that photons follow curved paths, so an observer can see more than half of the neutron star's surface at once. This light bending smooths out the pulsations that would otherwise result from hot regions rotating in and out of view. The degree of bending depends on the compactness of the star, which is the ratio of mass to radius. By modelling pulse profiles of thermal emission, astronomers can infer both the mass and radius, providing constraints on the dense matter equation of state. Many neutron stars show hotspots on their surfaces. These are small regions where the temperature is higher than average. Hotspots can form at the magnetic poles, where charged particles from the magnetosphere strike the surface. They can also arise in accreting systems wherein falling matter is funneled by magnetic fields onto small areas. As the star rotates, the hotspots move in and out of view, creating pulsations in the X-ray flux. Missions such as NICA have exploited this effect to measure neutron star sizes with high precision. By analysing the detailed shape of the pulse, taking into account light bending and rotation, researchers can reconstruct the star's surface geometry. The surface composition may change over time. In isolated neutron stars, heavy elements can sink, leaving a surface dominated by lighter elements such as hydrogen or helium if any remain. In accreting neutron stars, fresh material continually falls in and undergoes nuclear burning, producing heavier nuclei that alter the atmosphere. These changes affect the emergent spectrum. Understanding which elements dominate at the surface is therefore essential for interpreting observations correctly. Temperatures at the surface are typically in the range of hundreds of thousands to millions of degrees, far hotter than any planet but cool compared to the billions of degrees in the newborn stage. These temperatures produce X-ray radiation that is detectable across interstellar distances. The thermal radiation is one of the few direct signals from the star's surface, so careful modelling of the atmosphere is needed to translate observed spectra into accurate measurements of radius and temperature. Different compositions produce different spectral shapes, and magnetic fields further modify them. The surface and atmosphere also interact with the star's surrounding environment. In pulsars, charged particles accelerated in the magnetosphere strike the surface, heating polar caps and producing additional X-ray emission. In magnetars, magnetic stress can fracture the crust, releasing bursts of energy that heat the surface locally. These events can temporarily change the thermal emission, producing variations that fade as the star cools again. Observations of such outbursts provide valuable information about both the crust and the magnetosphere. General relativity ensures that the star's surface is one of the most extreme places where physics can be observed. The gravitational redshift of photons provides a direct test of strong gravity. The bending of light allows measurements of compactness. The modification of atomic processes by ultra-strong magnetic fields demonstrates quantum electrodynamics in regimes unreachable on Earth. Each of these aspects makes the surface and atmosphere a unique laboratory. Observations continue to refine our understanding. NICA has measured pulse profiles from several pulsars with such accuracy that constraints on the radius have reached uncertainties of only a few %. These results are consistent with radii around 12 kilometers, in agreement with gravitational wave observations of mergers. X-ray spectroscopy has revealed absorption features that may correspond to proton cyclotron resonances, though interpretation remains debated. Cooling curves of young neutron stars reveal how surface temperatures change with time, providing clues to heat transport through the crust and atmosphere. The study of neutron star surfaces is not only about measuring numbers, but also about understanding processes. Radiation emerging from the surface carries the imprint of matter, compressed far beyond laboratory conditions. Hotspots trace the geometry of magnetic fields. Light bending encodes the compactness of space-time. Spectral lines reveal the strength of fields at the surface. Together, these phenomena create a direct observational link to the hidden interior. Among the many kinds of neutron stars, magnetars are among the most extraordinary. A magnetar is defined not by its mass or spin, but by the strength of its magnetic field. While most neutron stars have surface magnetic fields of about 1 trillion Gauss, magnetars exceed 1 quadrillion Gauss. To put this in perspective, Earth's magnetic field is less than 1 Gauss. The difference is so vast that physical processes near a magnetar cannot be compared to any ordinary astrophysical object. The field is strong enough to dominate the behavior of matter radiation and even the vacuum of space itself. The origin of magnetars is still debated. One idea is that they are born from massive progenitor stars that were already rapidly rotating and had strong magnetic seeds. During the collapse that forms the neutron star, a dynamo effect could operate in the convective interior, amplifying the magnetic field to extreme strengths. Another possibility is that magnetic flux from the progenitor star is simply conserved and concentrated as the core shrinks. Though this alone seems insufficient to reach the observed values, the dynamo model explains why magnetars may be preferentially young, as the amplification requires rapid initial rotation. The field strength of a magnetar has far-reaching consequences. In such conditions, atoms cannot exist in their usual form. Electrons are squeezed into thin tubes along magnetic field lines, and radiation becomes polarized. Quantum electrodynamics predicts that the vacuum itself becomes birefringent under such fields, meaning that empty space behaves like a material that splits light into different polarizations. This vacuum birefringence effect has been tentatively observed in the polarized light from magnetars, providing a rare test of quantum field theory in extreme conditions. Magnetars are most famous for their bursts and flares. The crust of a neutron star, though rigid, is under constant stress from the shifting magnetic field. In magnetars, the stress becomes so great that the crust cracks. When it does, energy stored in the magnetic field is suddenly released. These releases appear as bursts of X-rays and gamma rays. Short bursts may last only fractions of a second, but giant flares can outshine all other X-ray sources in the sky. The most powerful giant flare recorded from a magnetar in 2004 briefly affected Earth's upper atmosphere despite originating from across the galaxy. The mechanism of these flares involves both the crust and the magnetosphere. When the crust breaks, magnetic field lines can reconnect, similar to but vastly more powerful than solar flares. This reconnection accelerates particles and produces high-energy radiation. The energy release can be staggering, equivalent to the sun's total output over thousands of years. Such flares provide insight into the storage and release of magnetic energy on cosmic scales. Magnetars also exhibit persistent X-ray emission even between bursts. This emission is believed to come from the decay of their strong magnetic fields. As the field decays, it heats the crust and surface, producing a steady glow. Over time, this glow fades as the magnetic energy is depleted. The lifetime of a magnetar in this active phase is thought to be only about 10,000 years, much shorter than the typical lifetime of a radio pulsar. This brevity explains why magnetars are relatively rare, with only a few dozen identified in the Milky Way. Some magnetars are observed as soft gamma repeaters producing repeated bursts of soft gamma rays. Others are detected as anomalous X-ray pulsars with steady X-ray emission, brighter than expected from their spin-down energy. Both types are now understood to be manifestations of the same underlying object, a neutron star with an ultra-strong magnetic field. The different observational categories reflect differences in activity and viewing geometry, rather than distinct classes. The magnetic field also shapes the magnetosphere around the star. Charged particles are trapped on field lines, forming twisted structures that can store energy. When these structures untwist or reconnect, bursts occur. The interaction of the magnetosphere with the crust is complex, but it is essential to understanding magnetar activity. Theories continue to refine how stresses build and how they are released. The discovery of fast radio bursts has introduced a new possible role for magnetars. These millisecond flashes of radio waves originating from far beyond our galaxy are among the brightest radio events in the universe. While their origin is still debated, some fast radio bursts have been linked to magnetar activity, particularly after a magnetar in our own galaxy produced a similar radio burst in association with an X-ray flare. This suggests that at least some fast radio bursts are powered by magnetars, though whether all remains uncertain. Observationally, magnetars are identified through their long spin periods, typically between 2 and 12 seconds, and their rapid spin-down rates. These measurements imply extremely strong magnetic fields. Their X-ray spectra often show both thermal emission from the surface and non-thermal components from magnetospheric processes. Polarization measurements may reveal signatures of vacuum birefringence. Each of these clues helps build the case for their extraordinary fields. The study of magnetars pushes the boundaries of multiple areas of physics. It tests nuclear physics through crustal stresses, quantum electrodynamics, through vacuum polarization, plasma physics, through magnetospheric activity, and astrophysics through their role as potential sources of fast radio bursts and gravitational waves. They are laboratories where theories can be confronted with phenomena unreachable on Earth. Magnetars are rare but powerful reminders of the diversity of neutron star behavior. By understanding how magnetic fields shape their evolution and activity, astronomers gain insight not only into neutron stars but into the role of magnetic energy in the cosmos. Among the many manifestations of neutron stars' pulsars are the most widely studied and the most iconic. A pulsar is a rotating neutron star whose magnetic axis is not aligned with its rotation axis. Beams of electromagnetic radiation are emitted along the magnetic poles, and as the star spins, these beams sweep across space. If one of the beams crosses Earth, an observer detects pulses of radiation at every rotation. The regularity of these pulses is so precise that pulsars were initially mistaken for artificial signals when they were first discovered in 1967. Today, thousands are known across the galaxy, providing a wealth of information about neutron star physics. The origin of pulsar emission lies in the star's magnetic field and rapid rotation. The rotating magnetic field generates strong electric fields that accelerate charged particles in the magnetosphere. These particles, primarily electrons and positrons, stream along the curved magnetic field lines and emit radiation. Different mechanisms contribute, including curvature radiation, synchrotron radiation, and inverse Compton scattering. The result is a coherent radio beam that can be detected across interstellar distances. In addition to radio emission, many pulsars are also observed in X-rays and gamma rays, with emission zones located at higher altitudes in the magnetosphere. The beam structure of pulsars is complex. Some pulsars emit single beams, others show double peaks, and some reveal more intricate patterns. The shape of the pulse profile depends on the geometry of the magnetic and rotation axes and on the observer's line of sight. This geometry explains why not all neutron stars are visible as pulsars. The beam may never cross Earth, or the emission may be too weak to detect. Thus, the observed population of pulsars represents only a fraction of all existing neutron stars. Pulsars slow down gradually over time as rotational energy is converted into electromagnetic radiation and particle winds. The rate of spin down depends on the strength of the magnetic field and the rotation period. By measuring the period and its derivative, astronomers can estimate a pulsar's age and magnetic field strength. Young pulsars, such as the one at the center of the Crab Nebula, spin rapidly, and lose energy quickly powering bright nebulae. Older pulsars spin more slowly and emit more faintly. Eventually, as the rotation slows further, the emission mechanism ceases and the pulsar becomes undetectable. This end stage is called the pulsar death line. Despite the gradual slowdown, pulsars remain highly stable clocks. Their rotation is so regular that their pulses can be predicted to within microseconds over long timescales. This precision makes them useful tools for astrophysics. Pulsar timing arrays use networks of pulsars to detect low-frequency gravitational waves by monitoring correlated variations in pulse arrival times. Millisecond pulsars, which spin hundreds of times per second, are especially valuable because of their extreme stability. They rival atomic clocks in precision and can be used to probe the fabric of space-time itself. Pulsars also show sudden irregularities in their rotation called glitches. These glitches, typically seen in young pulsars, are believed to originate from interactions between the crust and the superfluid interior. When pinned vortices in the superfluid suddenly move, angular momentum is transferred to the crust, causing the star to spin slightly faster. The study of glitches provides a unique probe of the otherwise inaccessible interior. Each glitch is like a seismological event revealing the star's internal dynamics. Another fascinating aspect of pulsars is their emission across the electromagnetic spectrum. Radio observations dominate because pulsars were first discovered in that band and are most numerous there. However, X-ray and gamma-ray pulsars reveal high-energy processes in their magnetospheres. Some pulsars are visible in optical light, though very faintly, and only a few have been detected this way. Multi-wavelength observations allow astronomers to build comprehensive models of how pulsar magnetospheres accelerate particles and radiate energy. Binary pulsars provide even more opportunity for study. In some systems, a pulsar orbits another neutron star or a white dwarf. By timing the pulses precisely, astronomers can measure relativistic effects predicted by general relativity, such as orbital decay due to gravitational wave emission. The first indirect evidence for gravitational waves came from the Hulse-Taylor binary pulsar, which showed orbital shrinkage exactly consistent with general relativity. Such systems continue to be important laboratories for testing fundamental physics. The diversity of pulsars is striking. Young pulsars in supernova remnants are energetic and erratic. Middle-aged pulsars are more stable and emit steadily. Old pulsars may be recycled by accretion from a companion star spun up to millisecond periods. Some pulsars are magnetaires with powerful magnetic fields, while others are ordinary radio pulsars with weaker fields. This diversity reflects the range of birth conditions and evolutionary paths that neutron stars can take. Pulsars also have practical astrophysical uses. Their signals can be used to measure the distribution of free electrons in the interstellar medium, since the pulses are dispersed as they travel through plasma. They can be used as navigational beacons in space, providing a natural coordinate system across the galaxy. They may even serve as probes of dark matter, if subtle anomalies in timing can be linked to interactions with unseen particles. From a broader perspective, pulsars represent one of the few ways that neutron stars reveal themselves directly. Their beams cut through space like cosmic lighthouses, offering regular signals that carry the imprint of extreme physics. The combination of magnetic fields, rotation, and radiation processes makes them unique among astrophysical objects. Each pulsar adds to the growing picture of how neutron stars behave, evolve, and influence their surroundings. The extraordinary regularity of pulsar rotation makes any sudden deviation noticeable. Yet astronomers have long observed abrupt changes in pulsar spin events known as glitches. A glitch is a sudden increase in rotational frequency, often followed by a slower relaxation back toward the previous spin-down trend. These events are not random noise but clear measurable signatures of processes taking place inside the neutron star. They provide one of the few direct observational windows into the dynamics of the interior, particularly the coupling between the crust and the superfluid layers beneath it. The standard picture of a glitch begins with the fact that the outer crust of the star rotates as a rigid body, slowing gradually as energy is lost through electromagnetic radiation. Beneath this crust lies a superfluid of neutrons threaded by quantized vortices that carry angular momentum. In a perfect superfluid, these vortices would move outward smoothly as the star spins down, transferring momentum to the crust. However, in neutron stars, the vortices are thought to become pinned to the nuclear lattice of the crust. While pinned, they cannot move outward, and the superfluid retains more angular momentum than the slowing crust. Over time, a differential builds up between the superfluid rotation and the crustal rotation. Eventually, some vortices unpin, suddenly releasing angular momentum into the crust. The result is a sudden spin-up of the observable surface, a glitch. The magnitude of glitches varies widely. Some involve fractional changes in spin frequency, of only 1 part in a billion, while others are much larger, on the order of 1 part in a million. The most famous glitching pulsar is the Vela pulsar, which exhibits large glitches roughly every few years. Each event provides new information about the coupling between the crust and the superfluid. The relaxation phase that follows a glitch, during which the spin returns slowly toward the long-term trend, offers clues about the viscosity and dynamics of different layers inside the star. The study of glitches is not only about rotational dynamics, they also shed light on the strength and structure of the crust. The forces required to unpin vortices and transfer angular momentum depend on the rigidity of the lattice and the properties of nuclear pasta deeper down. Observations of glitch sizes and frequencies therefore provide indirect constraints on the composition of the inner crust. They may even point to differences between stars of different ages, since young neutron stars tend to glitch more frequently than older ones. Not all timing irregularities are glitches. Pulsars also exhibit timing noise, which appears as random wanderings of the pulse phase over long timescales. This noise is not as sudden or dramatic as glitches, but it too may be linked to interior processes. It could arise from slow changes in superfluid coupling from magnetospheric variations, or from complex interactions between the crust and core. Distinguishing between timing noise and glitches is important for building accurate models of pulsar behavior. Another category of irregularity is the microglitch small and rapid events that are only detectable with highly precise monitoring. These may represent localized unpinning of a small number of vortices or small-scale shifts in magnetospheric currents. The continuum of behavior from microglitches to giant glitches suggests a wide range of scales for angular momentum transfer. Each event adds to the statistical picture of how neutron stars manage their internal stresses. Glitches also provide opportunities to test fundamental physics. The sudden transfer of angular momentum involves interactions between quantum vortices and nuclear matter under extreme conditions. Laboratory experiments cannot replicate such systems, so neutron stars are the only places where these processes can be studied. Models of glitch dynamics incorporate superfluid hydrodynamics, quantum pinning forces, and nuclear physics. Observational data from decades of pulsar timing are essential to constrain these models. The coupling between the neutron superfluid and the crust is a central issue. If vortices are strongly pinned, large glitches should be expected as stress builds over long intervals. If vortices are weakly pinned, smaller and more frequent glitches occur. Observations suggest that both regimes exist depending on the pulsar. Some pulsars like Vela produce large glitches at semi-regular intervals, while others show smaller, less predictable events. This diversity may reflect differences in temperature, magnetic field, and crustal structure. Glitch activity also evolves over time. Young pulsars still hot and dynamic glitch more often. As neutron stars cool and age, the superfluid dynamics may change, reducing glitch frequency. Yet even old pulsars occasionally display glitches, demonstrating that the processes persist across millions of years. The balance between crustal rigidity, superfluid pinning, and magnetic stresses likely changes with age, altering the star's rotational irregularities. Astronomers track glitches with long-term monitoring campaigns. Large radio telescope arrays observe pulsars, regularly building continuous timing records that can capture sudden events. Space-based X-ray observatories also contribute, particularly for young pulsars with strong X-ray emission. The precision of these measurements allows detection of even the smallest shifts in rotation. Over time, these records accumulate into catalogues of glitches, enabling statistical studies of their distribution across the pulsar population. Glitches may also interact with magnetospheric phenomena. Some observations suggest that a glitch can trigger changes in radio emission, altering pulse profiles or emission modes. This indicates that the internal dynamics of the star can influence its magnetosphere, linking deep physics with observable radiation. Understanding these connections is a developing area of research. From a theoretical standpoint, glitches are reminders that neutron stars are not static objects. They evolve, adjust, and sometimes reconfigure suddenly. The rigid crust and the superfluid interior are in constant tension, and glitches are the moments when that tension is resolved. By studying them, scientists learn not only about the specific stars that glitch, but about the general properties of dense matter. In the long run, continued monitoring of pulsars will expand the database of glitches and refine theoretical models. With more sensitive instruments, smaller and rarer events may be detected. As gravitational wave astronomy matures, it may even be possible to observe gravitational signals associated with large glitches, though these would be faint. The synergy of different observational methods promises a deeper understanding of one of the most distinctive signatures of neutron star physics. Some neutron stars rotate not only quickly but at extreme speeds hundreds of times each second. These objects are known as millisecond pulsars. Their rapid spin is not a property they are born with, but the result of a later stage of evolution. A normal pulsar slows down gradually as it radiates energy, but if it resides in a binary system and accretes matter from a companion, angular momentum can be transferred. Over millions to billions of years, this transfer spins the neutron star back up to enormous rotational rates. The process is often called recycling because it revives old slow pulsars and turns them into millisecond pulsars. The mechanism begins when a companion star evolves and expands. Material overflows its gravitational boundary known as the Roche lobe and forms an accretion disk around the neutron star. Gas in the disk spirals inward, releasing gravitational energy as heat and radiation. As the matter falls onto the neutron star, it brings angular momentum with it. Gradually, the neutron star's rotation accelerates. In some cases, the spin period is reduced to less than 2 milliseconds, meaning the star rotates over 500 times every second. At such speeds, the surface moves at a significant fraction of the speed of light. The recycling hypothesis is supported by several lines of evidence. Many millisecond pulsars are found in binary systems with low-mass white dwarf companions, exactly as expected if mass transfer spun them up. Transitional systems have been observed in which a neutron star switches between being an accretion-powered X-ray source and a radio pulsar, providing direct confirmation of the process. These rare transitional pulsars are critical because they show the mechanism in action, bridging the gap between theory and observation. Millisecond pulsars differ from ordinary pulsars not only in speed but also in stability. Their rapid rotation and low magnetic fields make them extraordinarily precise clocks. Timing observations show that their periods can be predicted with accuracies rivaling those of atomic clocks on Earth. This stability makes them ideal tools for probing astrophysical and cosmological phenomena. Networks of millisecond pulsars known as pulsar timing arrays are used to search for gravitational waves from supermassive black hole binaries. By comparing arrival times of pulses across the sky, astronomers can detect correlated variations caused by ripples in spacetime. The internal physics of millisecond pulsars is also of great interest. At such rapid spins, the centrifugal force at the equator approaches the point where it could disrupt the star. This sets a natural limit to how fast a neutron star can rotate before breaking apart. The fastest known pulsar spins at about 716 times per second. This is below the theoretical maximum, which is thought to be around 1000 to 1200 spins per second, depending on the equation of state. The absence of pulsars above this limit is consistent with expectations, but it also helps constrain the stiffness of matter inside the star. Accretion onto neutron stars can be directly observed through X-ray emission. In low-mass X-ray binaries where a neutron star accretes from a lighter companion, bursts of X-rays are seen. These bursts arise from thermonuclear explosions on the surface as accumulated material undergoes unstable fusion. Over time, the steady accretion spins the neutron star up. Once accretion ceases, the star may shine as a radiomillisecond pulsar with its rapid spin sustained. Observations of such binaries reveal the intermediate stages of recycling. Millisecond pulsars also provide laboratories for testing relativity. In binary systems, their stable timing allows precise measurements of orbital motion. Some of the most stringent tests of general relativity have come from millisecond pulsars in binaries with white dwarfs or other neutron stars. The timing precision allows the detection of effects such as Shapiro delay, where light passes through curved spacetime near a companion, and orbital decay due to gravitational wave emission. These tests confirm Einstein's theory to remarkable accuracy. Clusters of stars, especially globular clusters, are rich environments for millisecond pulsars. The high stellar densities in clusters make interactions and exchanges of companions common. As a result, globular clusters contain disproportionately large populations of millisecond pulsars. These systems provide natural laboratories for studying not only pulsars, but also stellar dynamics and evolution in dense environments. The electromagnetic emission of millisecond pulsars spans the spectrum. Most are observed in radio, but many also emit in gamma rays. The Fermi Gamma Ray Space Telescope has detected dozens of millisecond pulsars, revealing that they can be bright in high-energy bands, despite their relatively low magnetic fields. The gamma-ray emission likely arises from particle acceleration in the outer magnetosphere, where fields and rotation combine to drive energetic processes. Millisecond pulsars also have practical uses. Because they are stable clocks distributed throughout the galaxy, they can serve as a natural navigation system for spacecraft. By comparing pulse arrival times from several pulsars, a spacecraft can triangulate its position in space much like using GPS on Earth. This concept has been tested and shows promise for future deep space missions, where traditional navigation methods are limited. Despite their stability, millisecond pulsars can still exhibit irregularities. Some show small glitches, though much less frequently than young pulsars. Others show variations in pulse shape or intensity reflecting changes in magnetospheric conditions. These features remind astronomers that even the most stable neutron stars remain dynamic systems. The study of millisecond pulsars continues to expand. Surveys with large radio telescopes such as FAST in China and MEERKAT in South Africa are discovering new examples. Each discovery adds to pulsar timing arrays, improving the chances of detecting nanohertz gravitational waves. These waves, produced by orbiting supermassive black holes in distant galaxies, are expected to be revealed through the collective timing of millisecond pulsars across the sky. Early results already suggest the presence of a background of low-frequency gravitational waves. Millisecond pulsars are therefore not only fascinating astrophysical objects, but also essential tools. They test theories of dense matter relativity and magnetospheric physics, and they serve as detectors of gravitational waves and as navigational beacons. Their existence demonstrates the extraordinary ways that neutron stars can evolve recycling through accretion to become some of the most stable rotators in the universe. When a neutron star resides in a binary system, the flow of matter from a companion creates some of the most energetic astrophysical phenomena. This process, known as accretion, is governed by gravity magnetism and nuclear physics. Gas drawn from the companion forms an accretion disk heating to millions of degrees as it spirals inward. The inner edge of the disk interacts with the neutron star's magnetic field, and the fate of the infalling matter depends on the field strength. In stars with weak magnetic fields, the gas can reach the surface nearly uniformly. In stars with strong fields, the gas is funneled along magnetic field lines, crashing onto the poles and producing hotspots. The impact of accreting matter releases enormous energy. As gas falls onto the surface, it converts gravitational potential energy into heat and radiation. Because the neutron star's surface lies deep in a gravitational well, this energy conversion is extremely efficient. Even a small amount of matter can produce intense X-ray emission. This is why accreting neutron stars are among the brightest X-ray sources in the sky. They outshine entire galaxies in the X-ray band for brief periods. Some accreting neutron stars reveal themselves as X-ray pulsars. In these systems, the magnetic field channels the accreting matter onto localized spots at the poles. As the star rotates, the hotspots come into and out of view, producing periodic pulses of X-rays. These X-ray pulses provide direct evidence of accretion channeled by magnetic fields. By studying their pulses, astronomers learn about the geometry of the field and the distribution of matter in the magnetosphere. In other cases, accretion leads to thermonuclear explosions on the surface. When hydrogen and helium accumulate on the neutron star, they undergo unstable fusion once a critical pressure is reached. The result is a runaway reaction that burns the accumulated layer in seconds, releasing a burst of X-rays. These X-ray bursts can last for tens of seconds and repeat every few hours as new material piles up. Observations of such bursts have been used to study nuclear reactions at high densities and to probe the composition of the accreted material. Some bursts show oscillations linked to the star's spin, providing another way to measure rotation rates. There are even rarer and more extreme events called superbursts. These last for hours and are thought to result from carbon burning deep in the crust ignited under immense pressure. Superbursts are observed only occasionally, but when they occur, they demonstrate the complex nuclear processes at work beneath the surface. They also highlight how accretion continually transforms the crust and fuels deeper reactions. Accretion does more than produce bursts. It also heats the neutron star's crust over long timescales. As matter is pushed deeper, it undergoes electron captures, neutron emissions, and pyknonuclear fusion reactions. These processes release heat that can be observed when accretion halts. Some neutron stars alternate between accreting phases and quiescent phases. During quiescence, the crust cools and its thermal emission can be detected. By monitoring how quickly a star cools after an accretion episode, astronomers learn about the thermal conductivity and heat capacity of the crust. Such studies provide rare tests of matter under extreme pressure. The presence of a companion also alters the neutron star's spin. As material brings angular momentum, the neutron star can be spun up sometimes to millisecond periods. Many of the fastest known pulsars were recycled in this way. The link between accretion and millisecond pulsars is clear with transitional systems, observed switching between accretion-powered X-ray emission and radio pulsations. These objects prove that accretion not only fuels bursts, but also reshapes the star's long-term evolution. Binary accretion is diverse. Some systems involve massive companions shedding strong stellar winds. The neutron star captures part of the wind, leading to variable and irregular accretion. Other systems involve Roche lobe overflow, where matter streams directly into the neutron star's gravitational domain, forming a stable disk. The differences in companion mass and orbital configuration create a wide range of observational phenomena. Accretion is not always steady. In many systems, accretion occurs in bursts or cycles. Transient X-ray binaries are systems where the neutron star is faint most of the time but occasionally brightens dramatically. These outbursts occur when instabilities in the accretion disk cause sudden increases in mass flow. During outbursts, the neutron star may display X-ray pulsations, bursts, or quasi-periodic oscillations. When the outburst ends, the system returns to quiescence, allowing astronomers to study the cooling crust. Another striking phenomenon is the presence of kilohertz quasi-periodic oscillations in the X-ray emission of some accreting neutron stars. These oscillations are believed to arise from orbital motion at the inner edge of the accretion disk close to the neutron star's surface. Their frequency is often hundreds to over 1,000 cycles per second, provide direct probes of strong gravity. By interpreting these oscillations, scientists can estimate the mass and radius of the star, offering constraints on the equation of state. Accreting neutron stars also emit jets, narrow streams of matter, accelerated to near light speed and launched perpendicular to the accretion disk. These jets produce radio emission and can carry away large amounts of energy. The mechanism behind jet formation remains uncertain, but magnetic fields and rotation play central roles. Observing jets from neutron star binaries provides an opportunity to compare them with those from black holes and to understand the role of the central object's surface. Unlike black holes, neutron stars have a hard surface that affects how accretion energy is released. Magnetic fields shape every aspect of accretion. In strongly magnetized neutron stars, the magnetosphere truncates the accretion disk at some distance from the surface. Matter is then funneled along field lines, creating X-ray pulsars. In weakly magnetized stars, the disk can extend nearly to the surface, producing boundary layer emission, where the disk meets the star. These differences explain the variety of observed X-ray behaviors in different systems. Accretion also affects the star's long-term magnetic evolution. The inflow of material may bury the magnetic field beneath the surface, reducing its observable strength. Over time, the field may re-emerge as the accreted material spreads. This interplay between accretion and magnetism remains an active area of research, with implications for the formation of millisecond pulsars and the diversity of neutron star magnetic fields. Observations of accreting neutron stars come from many instruments. Space telescopes such as RxTE, Chandra, XMM Newton, and NITSA have recorded bursts, oscillations, and persistent X-ray emission. Radio telescopes track the reappearance of pulsations when accretion halts. Optical observations detect the companion stars and accretion disks. By combining all these data, astronomers build a comprehensive picture of how accretion transforms neutron stars. Accretion is therefore not a secondary detail, but a central process in neutron star evolution. It powers luminous bursts, alters crustal composition, spins up old stars, and provides natural laboratories for nuclear and gravitational physics. Each accreting system adds to the understanding of how neutron stars grow, change, and interact with their environments. When two neutron stars orbit each other in a close binary, their mutual gravity locks them in an intricate dance that can last millions or even billions of years. Over time, the orbit gradually shrinks due to the emission of gravitational waves. This slow spiral eventually culminates in a cataclysmic merger, one of the most powerful events in the universe. Such mergers are not only spectacular astrophysical phenomena, but also vital to understanding the origin of heavy elements and the behavior of matter at nuclear densities. The loss of orbital energy through gravitational waves was first confirmed indirectly by the Hulse-Taylor binary pulsar discovered in 1974. Precise timing of its pulses revealed that the orbit was decaying at exactly the rate predicted by general relativity. Decades later, direct detection of gravitational waves by LIGO and Virgo provided unambiguous confirmation. In 2017, the merger of two neutron stars was observed both in gravitational waves and across the electromagnetic spectrum. This event, known as GW170817, marked the beginning of multi-messenger astronomy, where cosmic events are studied through both gravitational and electromagnetic signals. As neutron stars spiral closer, tidal forces distort their shapes. These tidal deformations affect the gravitational wave signal, encoding information about the internal structure of the stars. The stiffer the equation of state, the less the stars deform. By measuring the waveform carefully, astronomers can place constraints on the compressibility of nuclear matter. The inspiral phase therefore provides not only a test of relativity, but also a probe of the physics of dense matter. When the stars finally collide, the outcome depends on their combined mass. If the mass exceeds the maximum stable neutron star mass, the merged object collapses quickly to a black hole. If the mass is lower, a hypermassive neutron star may form temporarily supported by differential rotation and thermal pressure. Such an object may survive for milliseconds to seconds before collapsing. The brief life of this hypermassive star can power additional electromagnetic signals, including short gamma-ray bursts and kilonova emission. The kilonova arises from material ejected during the merger. As the stars collide, some matter is thrown outward at high velocity. This ejector is rich in neutrons and undergoes rapid neutron capture known as the R process. Through this process, heavy elements such as gold, platinum, and uranium are synthesized. The radioactive decay of these freshly forged nuclei powers an optical and infrared transient lasting days to weeks. The kilonova observed following GW1708-7 provided the first direct evidence that neutron star mergers are major sites of heavy element production in the universe. Short gamma-ray bursts are another outcome of neutron star mergers. These bursts last less than 2 seconds and are among the most luminous explosions observed. The prevailing model suggests that they originate when a black hole forms and drives a relativistic jet. If the jet is aligned with Earth, a gamma-ray burst is observed. In GW170817, a gamma-ray burst was detected shortly after the merger, though it was weaker than typical bursts, likely because the jet was not pointed directly at Earth. This association confirmed long-standing theories linking short gamma-ray bursts to neutron star mergers. The multi-messenger observations of GW170817 transformed astrophysics. Gravitational waves provided the chirp signal of the inspiral constraining the masses and tidal deformabilities. Gamma rays revealed the jet. Optical and infrared observations tracked the kilonova and its evolving colours, which reflected the composition of the ejecta. Radio and X-ray observations followed the afterglow as the jet interacted with surrounding material. Together, these signals painted a comprehensive picture of the merger. Such events provide laboratories for testing relativity nuclear physics and nucleosynthesis all at once. Future observations will refine this picture further. Each new merger adds to the sample of tidal deformability measurements, constraining the equation of state. Kilonova light curves can be compared across events to quantify how much heavy material is produced. Statistical samples of mergers will reveal whether most R-process elements originate from these events, or whether core collapse supernova also contribute significantly. Gravitational wave detections from multiple observatories will improve sky localization, enabling faster follow-up across the electromagnetic spectrum. The dynamics of mergers also raise important theoretical questions. How much matter is ejected dynamically during collision versus through winds from the remnant disk? What determines whether a hypermassive neutron star forms and how long it survives? How do magnetic fields evolve during the violent merger? Numerical simulations combining general relativity, magnetohydrodynamics, and nuclear physics are essential for answering these questions. They remain challenging, requiring immense computational resources, but progress continues steadily. Mergers also provide opportunities for precision cosmology. By measuring the gravitational wave signal, astronomers can determine the distance to the event directly without relying on a cosmic distance ladder. When combined with redshift measurements from electromagnetic counterparts, this provides a way to measure the expansion rate of the universe, the Hubble constant. G-Dubber, Sapvia 8.7 already demonstrated this method, though uncertainties remain. With more events, gravitational wave standard sirens will become a powerful tool for cosmology. The role of neutron star mergers in shaping galaxies is profound. The distribution of heavy elements observed in old stars suggests that such mergers contributed to galactic chemical enrichment over billions of years. The presence of elements like europium and gold in the solar system is likely due to past mergers in the Milky Way. Thus, when two neutron stars collide, they do more than release energy. They see the cosmos with the ingredients for planets and life. Neutron star mergers also stand at the frontier of observational astronomy. They link gravitational wave science with traditional telescopes requiring coordination across the globe. They demonstrate the power of multi-messenger approaches where no single observation suffices, but together they reveal the full story. Each merger is both a violent ending and a creative beginning. Collapsing stars giving rise to new elements and new opportunities for discovery. One of the central challenges in neutron star research is determining their masses and radii with high precision. These two quantities together provide direct constraints on the equation of state of dense matter. A stiffer equation of state allows larger radii for a given mass, while a softer equation produces more compact stars. By comparing observational data with theoretical models, astronomers can exclude entire families of equations of state, narrowing the possibilities for what matter is like at several times nuclear density. The most reliable measurements of neutron star mass come from binary systems. When a neutron star orbits a companion, the gravitational interaction can be studied through timing or spectroscopy. In binary pulsars, the arrival times of pulses give exquisitely precise measurements of orbital motion. In some systems, relativistic effects such as the Shapiro delay extra time taken by light as it passes through the curved spacetime of a companion allow mass determinations with high accuracy. Several neutron stars have been found with masses around 2 solar masses using these methods. These discoveries immediately ruled out any equation of state too soft to support such heavy stars. Radius measurements are more difficult but can be approached through several techniques. One method is to analyze the thermal emission from neutron stars in quiescent X-ray binaries. In these systems, accretion has ceased, leaving the neutron star surface visible. By fitting models of the atmosphere to the observed spectrum, astronomers can infer the radius, though uncertainties about composition and distance can complicate results. Another method relies on photospheric radius expansion bursts, where thermonuclear explosions on the surface temporarily lift the photosphere. The observed luminosity at the Eddington limit provides constraints on the star's mass and radius. A breakthrough has come from X-ray pulse profile modeling. The NICE mission on the International Space Station has observed hotspots on rotating neutron stars. As the star spins, these hotspots move in and out of view, but strong gravity bends their light. The shape and amplitude of the observed pulses depend on the compactness of the star, that is, the ratio of mass to radius. By modeling the pulse profiles in detail, including general relativistic effects, NICE has measured radii too within a few percent. For example, PSR J030.04 was found to have a radius of about 13 kilometers, consistent with theoretical expectations. Gravitational wave observations provide an independent avenue. During the inspiral of 2 neutron stars, their mutual tidal deformations leave an imprint on the gravitational waveform. The size of this tidal effect depends on the star's radius and equation of state. Analysis of GW1 0817 showed that typical neutron stars must have radii in the range of about 11 to 13 kilometers. This result aligns with NICE measurements, giving confidence that multiple methods are converging on the same answer. Measuring both mass and radius together is particularly powerful. For a given equation of state, there is a relation between these quantities, often shown as a mass-radius curve. Each observational data point either supports or challenges this curve. Heavy neutron stars around 2 solar masses demonstrate that matter must remain stiff enough at high densities to prevent collapse. Radius measurements near 1.5 solar masses constrain the behavior at lower densities. Together they pin down the possible shapes of the curve. The maximum mass of neutron stars is another key parameter. Observations of stars with about 2 solar masses already exclude many equations of state. If a neutron star heavier than about 2.3 or 2.4 solar masses were discovered, it would place even stronger limits. Conversely, if no stars above 2 solar masses exist, it would suggest that collapse to black holes occurs relatively early. The boundary between neutron stars and black holes remains an important frontier. Uncertainties still remain in these measurements. Atmospheric composition affects thermal models and assumptions about magnetic fields and accretion. History can alter interpretations. Distance estimates can introduce error. For gravitational wave events, degeneracies between parameters can blur radius constraints. Nonetheless, the agreement between independent methods suggests that progress is steady. Precise mass and radius measurements also test relativity. Alternative theories of gravity predict different mass-radius relations. Observations consistent with general relativity strengthen confidence in Einstein's theory, while any systematic deviations could hint at new physics. So far, data agree with relativity, but more measurements are needed to probe extreme regimes. Neutron star masses and radii are not only academic questions. They affect astrophysical phenomena from pulsar timing to merger outcomes. The maximum spin rate of a neutron star depends on its radius. The type of remnant formed after a merger depends on the maximum mass. The brightness and composition of kilonovae depend on how matter behaves under compression. Thus, by measuring these fundamental properties, astronomers link the microphysics of dense matter to the macroscopic behavior of galaxies. In the near future, improved instruments promise to refine these constraints further. Upgraded gravitational wave detectors will capture more neutron star mergers with higher precision. New X-ray missions will extend NICE's work measuring more stars with better resolution. Large radio surveys will continue to find heavy pulsars expanding the known mass range. The combination of these approaches will narrow the uncertainty around the true equation of state. The determination of neutron star mass and radius is therefore one of the clearest paths toward understanding the nature of matter under extreme conditions. By gathering precise measurements, astronomers are gradually closing in on the answer to what lies inside these remarkable stars. Across the galaxy, neutron stars are born, evolve, and eventually fade into quiet remnants. Their population is diverse, reflecting the different paths that massive stars can take in their final stages. Some neutron stars emerge as energetic young pulsars spinning rapidly and shining brightly in radio X-rays or gamma rays. Others begin life with magnetic fields so intense that they become magnetars, producing bursts and flares. Some reside in binaries, accreting matter from companions and revealing themselves as X-ray sources or evolving into millisecond pulsars. Each type represents a stage or outcome in the life cycle of these compact objects. The distribution of neutron stars across the Milky Way is not uniform. Because they are born from massive stars which form and die quickly, neutron stars are concentrated in regions of active star formation, such as the galactic disk. Their high birth velocities, however, mean that many are kicked far from their birthplaces. Some race through the galaxy at hundreds of kilometers per second, even reaching its outer halo. Over millions of years, these fast-moving neutron stars can populate distant regions, carrying their properties with them. Observations of isolated neutron stars moving supersonically through interstellar gas provide striking evidence of these natal kicks. The long-term evolution of neutron stars depends on their initial conditions and environment. A solitary neutron star without a companion cools steadily over time. In the first million years, it shines in X-rays as it loses thermal energy. Later, it becomes too cool to detect, fading into darkness. If it was a pulsar, its emission ceases once it crosses the death line, when the rotation and magnetic field can no longer sustain particle acceleration. Such stars remain as invisible remnants, detectable only through gravitational effects on nearby matter. The galaxy is thought to contain hundreds of millions of these silent neutron stars, most of them undetected. In contrast, neutron stars in binaries have more complex paths. Accretion from a companion can keep them hot, alter their crust, and spin them up into millisecond pulsars. These recycled pulsars can remain detectable for billions of years, outlasting the active lives of ordinary pulsars. Some binaries involve two neutron stars which eventually merge, producing gravitational waves and kilonovae. Others involve a neutron star and a black hole with different outcomes depending on the balance of masses. The diversity of binary interactions ensures that neutron stars influence their surroundings in many ways, from enriching the galaxy with heavy elements to powering bursts of high-energy radiation. The eventual fate of neutron stars also depends on their mass. If accretion or merger pushes a neutron star above the maximum mass supported by the equation of state, it collapses into a black hole. This collapse may be quiet or may produce bursts of radiation depending on circumstances. Thus, neutron stars can serve as the stepping stones in the cosmic progression from stars to black holes. Those that avoid collapse may persist indefinitely, cooling and spinning down but remaining intact. The oldest neutron stars in the universe could be nearly as old as the Milky Way itself, silent witnesses to billions of years of cosmic history. Comparisons with other compact objects highlight the unique role of neutron stars. White dwarfs supported by electron degeneracy pressure represent the end point for less massive stars. They are larger with radii of thousands of kilometers and less dense, though still extreme by earthly standards. Neutron stars are far smaller and denser, bridging the gap between white dwarfs and black holes. Black holes represent collapse beyond the limits of degeneracy pressure, where gravity overwhelms all resistance. Neutron stars sit in between, where quantum mechanics, nuclear forces and relativity balance in a delicate equilibrium. The population of neutron stars also provides insight into galactic evolution. Each neutron star traces back to a massive progenitor. By studying their numbers, velocities and distributions, astronomers learn about the rate of massive star formation, the efficiency of supernova explosions and the processes that enrich galaxies with heavy elements. Pulsar surveys, X-ray observations and gravitational wave detections together create a census of neutron stars that extends from young active remnants to ancient invisible ones. Open questions remain about their life cycles. How do magnetic fields evolve over millions of years? What determines whether a neutron star becomes a magnetar, an ordinary pulsar or a millisecond pulsar? How often do binary neutron stars merge, and how much R-process material do they contribute to galaxies? These questions link neutron stars not only to their own physics, but to the broader story of the cosmos, from the origin of elements to the structure of space-time. As observational capabilities expand, the study of neutron star populations becomes more complete. Radio telescopes like FAST and MEERKAT discover new pulsars, while space missions like NICER refine radius measurements. Gravitational wave observatories detect mergers revealing populations invisible to traditional telescopes. Each new detection adds another piece to the puzzle, showing how neutron stars are born, evolve, and end their lives. The diversity of outcomes emphasizes that there is no single path for these stars, only a spectrum shaped by initial conditions and cosmic environments. In the long view, neutron stars are enduring but not eternal. Some collapse into black holes, some fade into invisibility, and others continue to shine as pulsars or magnetars. Collectively, they are fundamental to astrophysics. They link the deaths of massive stars to the enrichment of galaxies, the extremes of nuclear matter to the fabric of space-time, and the invisible workings of quantum mechanics to the observable universe. They are both relics of past explosions and engines of ongoing cosmic processes.